So hello everyone. So in continuation to multi-rate sampling, I am going to discuss non-integer sample rate conversion. Okay, so till now we have covered decimation, that was for downsampling. Okay, so what we have done, we have given input sample xn with frequency sampling rate f of s to a anti-aliasing filter first, anti-aliasing filter with cutoff frequency omega naught, that is equal to pi by m, and where m is the downsampling factor, and then we have given its output to a downsampler that will reduce its sampling rate by a factor m. The output will be ym with sampling rate fs new. Okay, so this fs new was equal to fs by m. Okay, and this m was an integer value. So what this downsampler was doing, it was removing m minus 1 samples, removed for each sample of xn, for each sample of x. Okay, so this is how it was reducing its sampling rate. This was the decimation process. And then we have discussed interpolation, that was for upsampling, increasing the sampling rate. So the input signal xn was first given to upsampler, that will increase its sampling frequency by factor L, and because of that spectral images will be created. So we have to use a low pass filter of cutoff frequency pi by L, and the output is yn with frequency fs new. The sampling rate, and sampling rate of input is fs. Okay, so this fs new was equal to L times fs, L times sampling rate increased. And how this was achieved? This was achieved by introducing L minus 1 samples were introduced between two adjacent sample of x, introduced between two adjacent samples of x. Okay, so what does it mean? Suppose this is xn for downsampling, and let's say m is equal to 2. Okay, so let's say m is equal to 3. So m minus 1 is 2. So this downsampler, if suppose this is selected, so next 2 is rejected. This one is selected, next 2 is rejected. Okay, so this is how the sampling rate was reduced by rejecting samples. And considering the upsample, suppose this is xn, and let's say L is equal to 3, so L minus 1 will be equal to 2. So between these two samples, two zeros, two new samples whose values are 0 will be introduced like this. So this is how the sample count increased. Okay, so information is lost in downsampling, and aliasing occurs, and no information is lost in upsampling, and spectral images were created. For this we have used low pass filter. Okay, so now consider a case. Okay, consider a case when I have a CD player. Okay, and it stores music. It stores music at 44.1 kilohertz. Okay, and I have a audio processor. Okay, that works at 48 gigahertz. Okay, so now suppose I want to transfer music from CD player to audio processor, or from audio processor to CD player. Okay, so in that case I have to convert the sampling rate. So let's say that I want to transfer the information from CD player to audio processor. Okay, so this is working at 44.1 kilohertz, this is working at 48 kilohertz. So for this I have to increase it sampling rate. Okay, so I have to use a sample rate converter, a sample rate converter. Its output will be given to the audio processor, and the factor by which the sampling rate should be converted is 48 divided by 44.1, that is equal to 1.0884. Okay, so we have to upsample the output signal of CD player by this factor, 44.1 multiplied by 1.0884. Okay, and till now we have upsampled or we have downsampled by using integer factors, and this is not a integer factors. So using the previously discussed method we cannot convert it. Okay, so we have to develop a new approach for the rational numbers. If the upsampling rate or upsampling factor or downsampling factor is a rational number. Okay, so let's see now what's the solution is for this. Okay, so we can combine the decimation and interpolation process. So combine decimation and interpolation process. Okay, this is the solution. And what are the steps? Step first is to find common integer factor. Okay, so I have 48 and 44.1, and this is also not a pure integer. Okay, if this is a pure integer then there will be no problem. Okay, so uh, I can convert it as, let's say, 160 by 147, that is also 1.0884, like this. Okay, now in second step, interpolate, or you can say upsample Okay, so let's say this is L and this is M. This is L by M because we have used L for upsampling, M for downsampling. Okay. After that, interpolate or upsample by factor L. Okay. So in this case, L is 160. Okay. So you have to upsample it by 160. Okay. So what it will do, what upsampler will do? So yeah, you will take the signal from CD player, you will upsample it by 160 and you will use a low pass filter. This is the interpolation process. Okay, and 159 zeros will be introduced between each pair of x, between each pair of xn and xn plus 1. Okay, now in third step, what you have to do, you have to decimate, you have to decimate, downsample by factor m, and m in this case is 147. Okay, so what it will do, it will reject 146 samples for each sample of x. Okay, so now you have to use decimeter. So first you have to use anti-aliasing filter, and then you will downsample it by factor 147, and this will be the output signal yn. So suppose the frequency of xn is fs, the frequency at this point will be 160 fs, the frequency at this point will be also 160 fs, the frequency at this point will be 160 fs, and the frequency at this point will be 160 by 147 fs, that is equal to 1.0884 fs. Okay, so first you have to perform the upsampling process, then you have to perform the downsampling process, and the cutoff frequency of this low pass filter will be pi by L, and the cutoff frequency of this anti-aliasing filter will be pi by M. Okay, so now these two filters can be combined like this: input signal xn and upsampling by factor L, a low pass filter. Okay, that is designed to eliminate spectral images and to avoid aliasing. Okay, so its cutoff frequency omega naught should be minimum of pi by L and pi by M. Okay, so suppose pi by L is greater than pi by M. Okay, and you have chosen omega naught as pi by M. So this filter will avoid aliasing, but still some spectral images will be there. And consider second case, if pi by m is greater than pi by l, and if you have chosen omega naught as pi by l. Okay, so spectral images will be avoided, but there will be aliasing. That's why you have to choose minimum of one of these two values. So automatically this two things will be avoided simultaneously. Then performing downsampling by m, and finally yn. So sampling rate fs at this point, l time fs at this point, l time fs, and at this time l by m time fs. Okay, so now suppose you want to change the sampling rate by factor 2 by 3. L by m is, let's say, 2 by 3. So you have to use the same approach. First you will upsample the signal by factor 2, then you will apply a low pass filter, and then you will downsample it by 3. Okay, whether it is 2 by 3 or 3 by 2 or 5 by 6 or any value L by m. L and m should be integer. Okay, so if something you have something like this 2.5 by 3, so you have to convert this into an integer. You can use 5 by 6. Okay, like this, because you cannot upsample it by 2.5, but you can upsample it by a factor of 5. So you have to convert this L by m. L by n again should be an integer. So this is the process. First you have to upsample, then you downsample it. Okay, so like this we have to do. Okay, now what if I interchange the position of interpolator and decimator? Okay, like I have first, instead of now upsampling, I will perform downsampling like this. Then I will use a low pass filter. After that I will upsample it. Okay, so let's see if its sampling rate is fs. Its sampling rate will be fs by m. Sampling rate at this point will be fs by m, and sampling rate at this point will be l by m fs. Okay, l by m fs. So mathematically the results are same. So which combination should we use? This or the one which just we have discussed, like this: upsampling, then low pass filter, and then downsampling and YF. So this is combination first. Okay, downsampling followed by upsampling, and this is combination 2 that we have discussed exhaustively. Upsampling followed by downsampling. Okay, so starting with this combination. Okay, suppose you are downsampling it first, and then you are passing to the anti-aliasing filter. This will both do the both things. It will avoid anti-aliasing and eliminate spectral images. Okay. So you know that when we perform downsampling, this kind of signal in frequency domain will become something like this. It will spread, and by applying filter, we will eliminate some of its portion. So there is a information lost in downsampling. Okay, and at this, then again it will eliminate spectral images. Okay, and then it will upsample. And now considering this case, the same signal will be compressed. Information will be not lost if we perform upsampling first. Okay, upsampling will give this. Then by performing low pass filter, okay, and at the same time there will be spectral images in the periodic range. So by this low pass filter, this can be eliminated. And then by applying upsampling, this will spread. So first it is already compressed. Okay, it is already compressed, then it will spread in this case. So now in the information lost, the chances of information lost is less because we have already shrinked it first, then we are spreading it. And in the first case, first it is spreading, then we are filtering, so information will be lost, and then this will be shrinking like this, something like this. Okay, and there may be case where information loss is very less than this, something like it will spread something like this. So the corner frequencies will be less rejected. Okay, so this combination is more suitable instead of this. Information reconstruction is better, the first combination. So this is not recommendable, this is recommended.